All right, today we're going to pull back the curtain on the world of manufacturing and look at something you can't see but that shapes almost everything around us. It's powerful, it's invisible, and it is absolutely essential. I mean, just think for a second about the parts in your phone or the blades inside a jet engine. The precision is just mind-boggling. And all of that comes down to controlling an invisible force that literally carves metal with microscopic accuracy. So what is this force? Well, it's called the cutting force. It's pretty much what it sounds like, the direct physical push that a tool uses to slice away material, sculpting a finished product from a solid block. Honestly, it's the unsung hero of manufacturing. And if you want to understand how things are made today, you have to understand this. Now, you might be thinking, okay, a force, it's just a push, right? Well, not exactly. It's actually way more complex than that. Cutting force isn't just one thing. It's a combination of several forces all acting at the exact same time. So let's take a look at the anatomy of the cut. So let's meet the key players here. First up, you've got the main cutting force. This is the heavy lifter, the powerhouse, doing most of the actual material shearing. Then there's the feed force, and that's what's pushing the tool forward along its path. The radial force is interesting. It pushes the tool away from the part. And finally, in something like drilling, you have the thrust force, which is all about driving that tool straight into the material. And what's so cool is that depending on the job, a different force takes the lead. You know, if you're turning a part on a lathe, it's all about that main cutting force. But when you're drilling a hole, suddenly the thrust force is king. It's what determines if you get a clean hole or a broken drill bit. And milling? Oh, that's a totally different beast. All the forces are jumping up and down like crazy as the little cutting teeth enter and exit the material. And that brings us to a really, really important point. These forces, they are never just sitting still. It's not a constant, steady push. It's more like a dynamic dance, this constant back and forth between the tool and the material. Yeah, the difference is huge. We might imagine this simple, predictable, static force, right? But the reality inside a machine is completely dynamic. It's a vibrant, oscillating signal that's changing constantly because of tiny vibrations, the material properties, and even how worn out the tool is. And all the most valuable information, well, it's hidden inside that complex signal. This is exactly why engineers are so obsessed with these fluctuations. Because, as researchers have found, if you can read these dynamic signals correctly, you can predict the stability of the entire process. You can stop something called chatter, which is this horrible destructive vibration that can totally ruin a part and shatter a tool in seconds. Okay, so this force is complex, it's dynamic, and it's super important. The next logical question is, how do you control it? Well, it turns out engineers have a few different levers they can pull to tune the force and get precisely the result they're looking for. The first lever is speed. And this is going to sound a little backward, but cranking up the cutting speed actually tends to reduce the overall forces. It's a fundamental principle behind what we call high-speed machining, and it's a real game changer. Now, the second lever is the feed rate, which is how fast you're advancing the tool into the material. And unlike speed, this one's pretty straightforward. The higher the feed rate, the bigger the bite the tool is taking, and that, in turn, raises the cutting forces by a lot. And hey, it's not just about speed and feed. There's a third, super critical lever, the shape of the tool itself. Something as simple as the sharpness or the angle of the cutting edge can completely change the physics of the cut and redirect those forces. It gives engineers another really powerful way to fine-tune the whole operation. So, we know what the force is, we know the main components, and we know how to control it. But how do you actually see this invisible dance while it's happening? Well, that's where some seriously cool technology comes into play. The way we measure this stuff has evolved like crazy. I mean, it started with these big external platforms called dynamometers, but now we can embed tiny little sensors right onto the tool holders themselves to get real-time data. And the absolute cutting edge, get this, is intelligent tool holders. We're talking about smart tools that can literally feel the force, interpret what it means, and even tell you when they're getting worn out, all by themselves. So, we've gone through all the theory, all the tech, but let's bring this all back down to earth. Why does mastering this invisible force really matter? What's the impact in the real world? Well, the payoff is just huge. When you understand and control cutting forces, you get parts with a smoother, more perfect finish. Your tools last way longer, your machines run more efficiently and don't break down, you prevent those catastrophic failures we talked about, and you achieve the kind of incredible precision and accuracy that our modern world absolutely depends on. So the next time you pick up your phone or see a plane fly overhead, just take a second and think about the invisible sculpture, that complex, dynamic dance of forces, all tuned and controlled with incredible skill that literally shaped the world you're living in.